Hello again, my physics students. This is Mrs. Buchanan, and this is flip video number 15. We are continuing our discussion of momentum, but let's revisit our big idea. Momentum is conserved for all collisions as long as external forces do not interfere. We will be covering learning objectives 3 and 4 with our video. Number 3, explain why an impulse is greater when an object bounces than when the same object comes to a sudden stop. If a flower pot falls from a shelf onto your head, you may be in trouble. If it bounces from your head, you may be in more serious trouble. Why? Because impulses are greater when an object bounces. The impulse required to bring an object to a stop and then throw it back again is greater than the impulse required merely to bring the object to a stop. Suppose, for example, that you catch the falling pot with your hands. You provide an impulse to reduce its momentum to 0. If you throw the pot upward again, you have to provide additional impulse. It takes a greater impulse to catch the pot and throw it back up than to merely just catch it. This increased amount of impulse is supplied by your head if the pot bounces from it. Let's take another example. A karate expert. This person strikes the bricks in such a way that his or her hand is made to bounce back, yielding as much as twice the impulse to the bricks. The fact that impulses are greater when bouncing takes place was used with great success during the California gold rush. The water wheels used in gold mining operations were not very effective. A man named Lester A. Pelton saw that the problem had to do with the flat paddles on the water wheel. He designed the curve-shaped paddle that we now see with those wheels. This paddle caused the incoming water to make a U-turn upon impact with the paddle. Because the water bounced, the impulse exerted on the water wheel was increased. Pelton patented his idea and probably made a whole lot more money from his invention called the Pelton wheel than any of the gold miners ever earned. Physics can indeed make you rich. Question: how does the impulse of a bounce compare to stopping only? Learning objective number 4. State and explain the law of conservation of momentum. We've discussed how a force applied during a time interval changes with the momentum of a ball. But in this discussion, in the discussion of our Newton's third law of motion, you learn that force is the result of interactions between objects moving in opposite directions. So let's take our tennis ball and a racket. The force of a tennis racket on the ball is accompanied by an equal and opposite force of the ball on the racket. Is the momentum of the racket therefore also changed? We also discussed Newton's second law, and you know that to accelerate an object, a net force must be applied to it. So we're going to talk about the same thing but in a little bit different way. If you wish to change the momentum of an object, exert an impulse on it. In either case, the force or impulse must be exerted on the object by something outside the object. Internal forces won't work. For example, the molecular forces within a basketball have no effect on the momentum of the basketball, just as a push against the dashboard of a car you're sitting in does not affect the momentum of the car. Molecular forces within the basketball and a push on the dashboard are internal forces. They come in balanced pairs that cancel within the object. To change the momentum of the basketball, or the car for that matter, an outside push or pull is required. If no outside force is present, no change in momentum is possible. Let's go back to our cannon and cannonball. The force on the cannonball inside the cannon barrel is equal and opposite to the force causing the cannon to recoil. Recall Newton's third law about action-reaction forces. These forces are internal to the system, comprising the cannon and the cannonball, so they don't change the momentum of the cannon-cannonball system. Before the firing Before the firing, the system is at rest and the momentum is zero. After the firing, the net momentum, or also known as the total momentum, is still zero. Net momentum is neither gained nor lost. Now let's consider the effects of internal and external forces carefully. Momentum, like the quantities of velocity and force, has both direction and magnitude. It's a vector quantity. Like velocity and force, momentum can be canceled. So although the cannonball in the preceding example gains momentum when fired, the recoiling cannon gains momentum in the opposite direction. The cannon-cannonball system gains none. The momenta, which is plural form of momentum, of the cannonball and the cannon are equal in magnitude and opposite in direction. Therefore, these momenta cancel each other out for the system as a whole. No external force acted on the system before or during firing. Since no net force acts on the system, there is no net impulse on the system, and there is no net change in the momentum. In every case, the momentum of a system cannot change unless it's acted on by external forces. A system will have the same momentum before some internal interaction as it has after the interaction occurs. When momentum or any quantity in physics does not change, we say it is conserved. The law of conservation of momentum describes the momentum of a system. The law of conservation of momentum states that in the absence of an external force, the momentum of a system remains unchanged. If a system undergoes changes wherein all forces are internal, as for example in atomic nuclei undergoing radioactive decay, cars colliding, or stars exploding, the net momentum of the system before and after the event is the same. So our question, what does the law of conservation of momentum state? One final thing I do want to talk about is momentum in a closed system. Under what conditions is the momentum of a system of two balls conserved? The first and most obvious condition is that at all times only two balls collide. No balls are lost and none are gained. A system that doesn't gain or lose mass is said to be a closed system. All the forces within a closed system are internal forces. The second condition required to conserve momentum of this system is that the only forces involved are internal forces. All the forces outside the system are external forces. When the net external force on a closed system is zero, it is described as an isolated system. No system on Earth can be said to be absolutely closed or isolated. That is, there will always be some interaction between a system and its environment. Often these interactions are small and can be ignored when solving physics problems. Systems can contain any number of objects. The objects can stick together or come apart in the collision. Again, under these conditions, the law of conservation of momentum states that the momentum of any closed system with no net external force does not change. This law will enable you to make a connection between conditions before and after an interaction without knowing any details of the interaction. So let's take one final example. You have a flask filled with gas and a closed stopper. It's a system with many particles. The gas molecules are in constant random motion at all temperatures above absolute zero, and they're constantly colliding with each other and with the walls of the flask. The momenta of the particles are changing with every collision. In a two-particle collision, the momentum gained by one particle is equal to that lost by the other. Momentum is also conserved in collisions between particles in the flask wall. Although the wall's velocity might change very slightly in each collision, there are as many momenta of particles to the right as to the left, and as many as down as up. So the net change in the momentum of the flask is zero. The total momentum of the system doesn't change, it is conserved. Thank you.